Welcome back to the last lecture of this course. I am very sure that you are pretty happy to reach the last lecture, and as I have told repeatedly before also, please send me feedbacks, constructive, destructive, positive, negative, whatever, at my email ID. So, typically when I take a classroom class in the last lecture, I do not teach anything new, but I do a recapitulation of what I have covered and also take questions from the students. Unfortunately, in a video course that is not possible, but we will try to do a reasonably good recapitulation of what we have covered in the last 40 lectures. And the thing I will try to impress upon you, where exactly the two aspects of the course, instability and patterning, merge, and how by understanding the physics of instability you can sort of create patterns which has the potential for, or how instability mediated patterning may be in conjugation with templating strategies, maybe in conjugation with the top down approaches, has the potential to be used as viable patterning techniques. Now, we have covered some aspects in the course on instability mediated patterning, but please do not understand or feel that these are the only settings in which instability mediated patterns or instabilities are manifested. Instabilities and associated pattern formation is possible in various other settings, which due to shortage of time and to keep the course content within reasonable limits I did not discuss. For example, you can always look at the self-organized structure formation in a polymer blend comprising miscible blends or immiscible blends. So, here blend is a simple system where you have two polymers maybe in the same solvent and you just spin coat. What happens is that during the spin coating process itself there can be a phase segregation, and you do not get a flat morphology like even if you coat on a flat surface, and therefore it sort of results in phase segregated structures. So, you can have structures forming with blends. You can have a look at some of the aspects. So, you have two polymers in the system, let us say the proportion is A is to B, and if you spin coat on a flat surface, you see some morphology. So, what happens is the relative proportion of the two polymers and the extent of surface coverage by each of the phases do not match. So, one of the phases which probably let us say 60-40, the phase which has a 40% volume fraction covers or more or less than 40% of the surface. So, therefore, the other phase, if this 40% thing is occupying more than 40%, then what happens is that the other phase which is 60%, that has to now, it is now more cramped. So, that sort of takes a higher topography. In contrast, if this 40% phase is occupying less than 40%, then that's the other remaining 60% phase is sort of more relaxed. So, that sort of takes a topography which is the height of which is lower. So, you can see a variety of instability in this type of settings. Then even with a homopolymer, something which I did not talk, but is very common, is an external field mediated instability. So, you have a film and you apply an electric field, let us say, across this film. So, this electric field sort of with an air gap. So, the configuration is pretty similar to elastic contact instability, but the only difference is that in an elastic contact instability the destabilizing field arises because of interfacial van der Waals interaction. Here you apply an additional field which can be an electric field, which can be a thermal gradient, which can be a magnetic field or whatever, and this application of this field eventually results in polarization of this dielectric film, which is a polymer film in a capacitor geometry, and therefore, if it is in a liquid state, it sort of aligns in the direction of the field, forming columns. So, this is what is known as EHD instability or electrohydrodynamic instability. And the advantage is that this again acts due to the externally applied field. The advantage is that you are applying an additional field from outside. So, you have the ability now to control the strength of the field, and therefore, you can destabilize films which are much thicker in the context that this type of films with this type of thicknesses will never show an instability, a spontaneous instability like dewetting. Okay. So, this is a very nice technique which has resulted in electrohydrodynamic lithography, and the advantage is, so you get columns or other types of morphologies depending on a whole lot of things like film thickness, the field strength, the gap, the relative ratio between the film thickness and the gap between the two electrodes and things like that. So, you can search in the internet. Ulrich Steiner at Cambridge University, Cavendish Lab, he is one of the pioneers in this field, and now others including in India, Ashutosh Sharma's group work on these areas. So, this type of instability is manifested in a viscous film, purely viscous film, or it can also be seen in a soft elastic film. So, since the field strength is strong, it can overcome sort of the stiffness or the additional restoring forces in an elastic film imparted by the physical crosslinks which are present. So, there are many, one can look into the whole lot of instabilities with evaporation induced instability, we briefly talked in the initial classes, look at the coffee stain effect. One can look into the pattern formation, associated pattern formation due to evaporation, as well as condensation, which are known as the breath patterns, where you just take out a cold surface and keep it in a humid environment, you see tiny droplets of water forming on the surface at a beautiful hexagonal closed back ordering. So, whole lot of things are there, and it is an advanced evolving area. So, it is not possible to really cover everything in a framework of a course. Textbooks are coming up, review papers are already available, some of which I have cited and you can sort of consult. Of course, the other thing we did not talk is the instability or the phase segregation of what is known as the block copolymers. So, block copolymer, unlike a blend where you mix two different polymers, block copolymer molecules are special. So, they sort of each of the molecule contains two blocks, each representing a different species. So, they also exhibit their own internal assembly. So, block copolymer molecules to a large extent behave like surfactants. So, there is internal self organization or self assembly depending on the system, depending on the composition, they have their own phase diagrams. And so, these are some of the things which we did not talk in this course, and I am giving you the clues. So, you can search some of them in the internet to get some idea about what they are. But even then, what we have talked is non-trivial, and it is pretty significant to sort of get started. And any one of you heading towards research in this particular area, I am sure will find the course to be pretty interesting. So, in the last lecture, I thought that I will give you a very little overview on another interesting topic, which is the fabrication of surfaces with gradient properties. Okay, and we have been doing some bit of work on this particular area lately. So, it is like this. So far, all the patterns that we have talked about, the generation of all the patterns by soft lithography, what we have talked about, the pattern dimension or the geometry or the morphology of the structures we have considered is uniform across the whole sample. Okay, so therefore, if you are looking, let us say, about the structural hydrophobicity of a patterned surface, you would expect that wherever you dispense the drop, you will get the same contact angle. Now, gradient surfaces are slightly different, where surface gradients are surfaces with a chemical or physical properties chemical or physical properties that change over a given distance. So, from one side to the other, let us say if the pattern topography or the morphology or even the chemical composition sort of varies, that is what is a gradient surface. So, there is a continuous variation of chemical or physical properties along the length of the surface. So, in that case, one might expect that on one end of the surface you have, so this is a regularly patterned regular patterns, I would say. Here it is a gradient surface. If you have fabricated, you can expect maybe at one side it is exhibiting a hydrophobic wetting regime, and the other side it may be hydrophilic, and in between there would be continuous variation in the contact angle. So, this is what is a gradient property. Gradients can be broadly divided into two types or categories. Of course, the first one is a chemical energy gradient, which eventually results there is a continuous variation. It boils down to the fact that there might be a continuous variation of the surface energy from one end to the other end of the film. So, and one end it can be completely very low surface energy, and on the other end it can be very high surface energy. So, in that case it will immediately translate to something like this. So, at the low gamma end you will have a high wettability, and at the high gamma end you will have low wettability. The other possibility, and let me also tell you that from the standpoint of fabrication, chemical energy gradients are more common, they are easier to fabricate, and there are quite a few methods are already available. What we will do, we will briefly tell you, I will briefly tell you some of the existing methods of fabricating these gradient surfaces, and then specifically take up one interesting case study by which one can fabricate a topographic gradient, which is based on a soft lithographic approach. So, that will make things easier to understand for you. The other one of course is a topography gradient. So, you have a continuous variation in surface topography, which can be regular topography or also partially ordered structures. So, it can be, if one is talking about a topographic gradient surface, with regular structures, let us say, if the structure we have talked most often is the grating. So, one can talk about a topographic gradient, so that from one end to the other, maybe the periodicity and the line width of the grating can change. That is the, you can have a continuous change in the periodicity, you can have a continuous change in the lateral dimension, you can have a continuous change in the number of features. I will write here. Something like that. You can have a continuous change in the feature height. Something like this. So, these are all examples of a topographic gradient with a regular structure. So, if you are talking in terms of, let us say, a simple grating, you can have a continuous variation of periodicity, continuous variation of line width or lateral dimension, continuous variation of the number of features, continuous variation of feature height, or a combination of these from one side to the other. Okay. You can also have a topographic gradient with let us say particles or other type of structures which may not be so regular. And so, let us see some of that, look at some of the methods by which you can make these gradients. But before that, let us have a quick look as what are the application of gradient surfaces. There are whole lot of application of gradient surfaces in biological applications, because of the fact that within a living body there are all sorts of gradients. So, for example, the transfer of oxygen or dissolved oxygen from blood to the individual cells is through the gradient in concentration. So, any transport across a membrane, whether it is a biological membrane or an artificial membrane, there is a gradient. So, gradients are existence everywhere, but gradient surfaces can sort of find a whole lot of application in tissue, controlled cell adhesion, protein adsorption, interfacial phenomena involving protein, cell, enzymes, biocompatibility issues, etc., etc. But most importantly, even in our engineering and physical experiments, they can be extremely useful for what is known as combinatorial analysis. So, this reduces the number of samples to a large extent, and also reduces the chances of sample specific errors. So, I will give you an example which will make you understand, give you an example from what we have already studied, which will give you an idea or make you understand what can be the utility of a gradient surface. Suppose you are studying duetting. Okay. And you would like to study the effect of substrate surface energy on duetting. We all know that substrate surface energy, the wettability sort of significantly influences the duetting pathway and instability. So, how would you typically study this? You would probably take 5 different samples with 5 different surface energies and then do spin coating under achievable identical conditions, and then you will individually study the duetting on each of the samples. So, this is your most likely approach if you are designing an experiment. So, firstly you need 5 sets of samples. Secondly, the most critical thing in any experiment, we all know from our school days that there will be some associated experimental error, and that experimental error can be in the form of variation of thickness. So, though you do sort of your spin coating under identical conditions for each of these samples, there might be some tiny variations in the thickness. So, therefore, what you might be studying the duetting of a 28.2 nanometer thick film on a gamma 1 surface, and in contrast you might be actually looking at a 26.4 nanometer thick film on a surface with a surface energy of gamma 4. So, but based on this you will assume that maybe you will look at all the samples and you will say that okay, we have studied the effect of dewetting of a 27 nanometer thick film on the effect of surface energy on a 27 nanometer thick film. Reality is that across individual samples, the way you have processed it, the thickness will vary from one sample to other sample. So, it is perfectly fine, lot of experiments are done in this fashion, but this all accumulates to the experimental error that you see, the errors in observation in experiments. In contrast, the conventional way of doing an experiment, firstly you need 5 samples, which can be expensive, number 1, and number 2 is that you sort of there might be uncontrolled error or unaccounted for unnoticed error in each of the samples, which varies from sample to sample. Instead of that, if you now can create, let us say, a surface where the surface energy varies from gamma 1 on one side to gamma 5 on other side. So, it is a gradient surface, and now you do a coating. So, the coating has been done at the same condition. So, whether it is 28.2 or 26.4 or 27.1, it is uniform across the entire sample. Okay. It is uniform across the entire sample. So, the error that was coming up because of the sample to sample variation or the error that is associated with sample to sample variation is completely nullified. Okay. So, you have whatever is your film thickness, you might have it is highly possible that you might have tried to coat a 27 nanometer thick film and you have resulted you have got a 28.1 nanometer thick film, that is highly possible, but that 28.1 nanometer thick film is uniform over the entire sample. Only the other thing is that instead of using 5 different samples, now you require only one sample. So, this only one sample gives you the liberty to study the effect of parametric variation. Okay. Only thing is that unlike these cases where maybe by coating of silane or some surface active molecules you could create different surface energies, here you have to create a gradient first, gradient surface energy or whatever you want. And the second important thing is you need to identify or distinguish or quantify the steepness of the gradient. So that you know the precise surface tension as a function of x, or the surface property, it can be gamma s or it can be any other surface property if it is topography. So, you can sort of have an idea. So, for example, if you are looking at a dewetting over this location, you must have an idea as to what type of surface energy configuration or what is the surface energy at this particular location. So, these are the only two things that are necessary. This type of an analysis is known as the combinatorial analysis, and as you can see, it significantly reduces the number of samples and less chance of sample to sample error. Now, so this is where one of the major advantages of gradient surfaces sort of come in experimental studies related to nanoscale or mesomechanical systems. So, the important thing that from the standpoint of fabrication that we need to understand is some techniques by which these gradients can be created, and as I have told that there can be two types of gradients, the chemical gradients or the topographic gradients. So, in general, the way a gradient is created is either the outermost surface layer of a substrate is gradually modified, for example, by irradiation or with a beam or chemical etching or whatever, or a layer is attached to the surface in a gradual manner. So, there are essentially two approaches. fabricating a gradient, mostly a chemical gradient, but it can also be that these approaches can be valid for a topographic gradient. One is, the first is that, so let us say this is the substrate, so this is the outermost layer of the substrate, okay. And what you do, you modify this outermost layer gradually. So, let us say you have a surface layer or SAM coated layer, and you understand that let us say by UV exposure you can tailor its surface energy. So, you have a SAM coated self assembled monolayer coated layer, let us say, which is giving you a contact angle of 110 degree. You know that if you expose it for 5 minutes, the contact angle will reduce to 90 degree. If you expose it for 10 minutes, it will reduce to 70 degree. 20 minutes, it will come down to 50 degree. So, if you can do something like a moving UV lamp source, which sort of exposes at this location, let us say for 5 minutes, but remains stationary here for 10 minutes, here for 20 minutes, here for 30 minutes, something like this, then what are you doing? You are essentially tailoring the extent of modification of the surface, okay? And in this way you can create a gradient. The other way of doing it is, if you are sort of, if you have a substrate, let us say, and you add some species to the surface in progressively varying numbers. So, suppose if you are adding some SAM self assembled monolayer molecules to the surface, and you add, let us say, this many numbers over here, you add more number of molecules here, you add even more number of molecules here, you attach even more number of molecules here, okay. So, that way also it becomes possible to create a gradient. So, let us talk about this concept again a little bit. So, here let us say this is over this zone, this is the extent of coverage with the SAM molecules. Here it is covered more, and here it is completely covered. So, let us say the SAM molecules are hydrophobic in nature, we understand. So, refer to our lectures on micro contact printing, where we talked about the nature of this silane or the thiol molecules. So, if you do something by which you progressively vary the number density of these molecules on the surface. So, progressively let us say the number density vis-a-vis the fractional coverage increases. So, this results in also in a gradient. So, these are the two broad approaches by which people are working on generating gradients. This is one of the simpler approaches, and majority of the chemical energy gradients that are fabricated even today are based on this approach, but this is also possible, and the case study we will give on a soft lithographic approach for generating a topographic gradient is based on this. Okay. So, wettability gradient, the most commonly used technique is for silanes, was developed in 1992 by Choudhury and Whitesides. All they did was they dissolved decycled trichlorosilane, I am sorry, I can't pronounce the name of the silane properly, in paraffin oil and let it evaporate. So, all they did was that this was a bath which contained the silane in an organic solvent, and the surface which was to be silanized was simply kept like this. So, as the molecules evaporated, so naturally the number of molecules that attached onto this substrate was more over these locations as compared to the far away corners. So, this resulted in a system like this. So, if the silane let us say the silanes were hydrophobic, so here the coverage was nearly complete, or it was more than a single layer, and here progressively the coverage reduced. So, if you now look at this sample or this glass slide, let us say it is a simple glass slide from the A end to the B end, here it is much the hydrophobic in nature as compared to lesser degree of hydrophobicity at this end. Okay, and there is a progressive variation, because as the it is kept vertical, so the diffusion path of the molecules is higher. So, here more number of molecules will attach, and then progressively less number of molecules will attach as you go further away from the source of the molecules. Okay. So, this results essentially in a surface with a chemical energy gradient, which results in a wettability gradient. And if you now place so there was a famous experiment they performed, that you place a drop of water like drop of water on this type of a surface, and it was kept on an inclined plane from the hydrophobic. So, A end was here and B end was here. So, ideally gravity will always pull the drop downward, but here they could show the Choudhury and Whiteside is a very famous paper which appeared in 1992 Science, that the droplet actually moved upward, and this upward movement was due to the imbalance in the forces due to surface tension acting on the liquid liquid contact line. So, what happens is, if you draw a drop for the Young's configuration, we always regard this is gamma s, gamma L and gamma SL. However, here the gamma s continuously varied. So, there was an imbalance in the along the contact line, which resulted in a passive driving force for the drop to move, and if the drop size was small, the inertial effects was not very high, and this allowed the drop to move uphill against the gravity. So, this is a pioneering experiment, and this has been showed by many others subsequently. There can be various other types of gradients, like electrochemical gradient, where the surface electrochemical potential gradient produces a spatial variation in the coverage of SAM, which results in a surface composition gradient. You can create an optical intensity gradient. So, you take some colloidal crystals with a thickness gradient prepared by dip coating. So, this is simple. So, you take a bath of colloidal crystals and you are withdrawing. This is in fact one of the very common ways of fabricating topographic gradient. So, what you do, you can dip it in a bath of nanoparticle or colloidal crystal, and you can do two things. So, as you withdraw, some particles will attach to the surface. Okay. Now, this rate of attachment can be controlled in two ways. Either you vary progressively the withdrawal speed, or what you can do, you can take a chemically patterned surface which offers different chemical properties on the surface, which results in a wettability contrast or the variation in the extent of adhesion, and that will lead to different number density of molecules attaching at different locations. So, this is one of the most popular ways of fabricating topographic gradient surfaces, and by varying the number density of the particles that are attaching. There has been various other approaches of making these type of surfaces. We present here a very simple approach. So, all that was taken, we all understand about the Silgard film now. So, we took a Silgard film was taken and it was subjected to a temperature gradient like this. So, it was just a normal hot plate and it was kept with two spacer blocks like this. So, different parts of the film surface were at different distance from the hot plate. So, if the film was cured for a finite or pre-cured for a finite duration, different locations of the film receive different extent of heat. And we all understand the thermal cross linking of a Silgard film. So, what happened is different locations, the extent of cross linking was different. So, let us say at the y1 end, which was closest to the hot plate, and the y2 end which was farthest from the hot plate, here the extent of cross linking was maximum. In contrast, here the extent of cross linking was minimum. So, eventually the extent of elasticity was maximum at this end as compared to the extent of elasticity was minimum at the other end. So, a pre-cured film for a definite duration, the pre-curing time can also be valid, had a progressive gradient in the extent of viscoelasticity. Okay. And what was done, that this film with a viscoelasticity gradient. So, in a normal soft lithography route or even in elastic contact lithography, you are imprinting a film which has uniform rheological properties. So, the film had uniform rheological property. In contrast, here we are now talking about a film which has a progressive gradient in its rheology. Okay. So, the level of viscoelasticity varies from one end to the other of the film. Now, if this type of a film is embossed or imprinted with a stamp under an uniform external pressure, you can still probably get a perfect negative replica on the entire stamp surface. But think of a scenario that you apply an external pressure, you imprint it, and then you withdraw the external force. So, now you have withdrawn the external force by imprinting a partially cured viscoelastic film. So, what happens? As we have talked in terms of elastic instability in the previous class, ideally once the external force is withdrawn, this film will try to relax back to its original flat morphology. But and that is because part of the energy that you have applied during this deformation, which is causing the surface deformation at the length scale of each of the features, okay, is stored within the elastic matrix. This is a viscoelastic film, so it is not a fully cross-linked film. So, part of the energy is lost as viscous dissipation in the form of viscous dissipation, and part of the energy is stored within the elastic matrix, which tries to relax back in the form of stress relaxation. So, now what happens is, as the extent of viscoelasticity varies from one end to the other, and let us say this is the y1 end, or let us say this is the y1 end where the extent of elasticity is maximum. So, the extent of recovery will be higher in this side of the film as compared to this side. And what will be the manifestation of the recovery or the stress relaxation? That will be, since the stamp is already placed on the surface. So, here you have a film, you had applied an external force and the external force is now withdrawn. Okay. And here you have higher level of elasticity, here you have lower level of elasticity. So, since the part of the energy, since it is a viscoelastic film, and remaining part is withdrawn, is lost due to viscous dissipation. So, here the extent of energy that is stored within the as elastic deformation is higher, and therefore, the stress relaxation will be higher here, which will be in the form of pushing the stamp upwards. Okay. So, this location, at this location the stress relaxation will be more, and the film will push the stamp upward by a higher extent as compared to this location, and this eventually results in a film where you have a gradient in the feature height. Okay. So, it is because of this. So, this is a typical rheological response you can see for a sill guard. So, with time there is a progressive cross linking, so which translates in our case to the fact that the part of the film which has received more heat sort of is at a higher cross link state. So, the level of elasticity is higher. So, therefore, the stress relaxation will be higher there, and eventually once you allow the film to relax, it will result in structures with different gradients, with a gradient. Interesting thing is that here you can, if you look at the experimental configuration, we had used 2 spacer blocks. So, important thing to note, 2 spacer blocks were used. The important thing to note is the steepness of the gradient can be controlled by 2 ways. Firstly, by varying the height of the 2 spacer blocks. So, that is the first approach. So, you can have 2 different spacer blocks which will essentially result in variation of the steepness of the gradient in the viscoelasticity, and which will eventually transform into the steepness of the gradient of the final structure. The other interesting or important thing is that there is a second tuning parameter, and that tuning parameter is the pre-curing time. So, here you do a pre-curing. So, if your pre-curing time is less, then the film remains in a predominantly viscous state. In contrast, if your pre-curing time is more, then the film remains or progressively goes to a predominantly elastic state. So, by varying the pre-curing time, you can vary whether you would like to have your film during imprinting in a viscous state or in a gradually elastic state. So, if your pre-curing time is less, the film will be predominantly in a viscous state. So, the extent of viscous dissipation will be lower, will be higher. The amount of energy that will be stored in the form of elastic deformation will be lower, and then therefore, you will get a gradient surface, but with deeper or higher feature height. In contrast, if you sort of which is very clear from this particular graph. So, this is the pre-curing time, and you can see that with increase in the pre-curing time, you can, for all the pre-curing times, you indeed get a gradient, but as your pre-curing time sort of becomes higher, progressively the overall depth of the features sort of reduces. You can also take different configurations of the spacer heights and can further control the steepness of the gradient. With appropriate stamps with high aspect ratio, it becomes possible by this way to create this topographic gradient can get transferred to wettability gradients as well, and it is possible to achieve wettability gradients within the hydrophobic regime, for example, what you see here, or a gradient which ranges all the way from the hydrophilic to reasonably hydrophobic extent. So, this is just one example what I decided to give you of how to actually implement or fabricate a topographic gradient surface, but there are very many ways to fabricate it but this is one rare example I must say where a simple soft lithographic approach has been used to fabricate a topographic gradient, and more importantly that this gradient is created in a one step method. Okay. Because majority of the topographic gradients, the patterns topographic gradient surfaces one wants to generate, it is typically a two step process. Firstly, you fabricate a chemical wettability gradient, and then you attach particles to it in progressively varying numbers. Or of course, one can prepare custom tailored stamp or masters with progressively varying feature size and can create it. But then while discussing soft lithography, we have repeatedly talked that surfaces with or stamps with special stamps anyway have to be fabricated by some high end photolithography or other type of lithography techniques, and therefore they are expensive to implement. So, this is a very simple way that one single stamp can be used, and one can generate a topographic structure. I would strongly encourage you to look into other aspects of fabricating gradients or other methods of gradients which can be made, or what are the other techniques you can search in the internet. So, there are a whole lot of literature that is available. Again, fabricating gradients is a very advanced area where a lot of research is still going on, and as I have already told, there are lots of application. So, some of the methods require which are reported require sophisticated instruments like controlled exposure. There is a very popular method called flow coating. Okay, so where you can have a look at what is flow coating. It is a flow coater which allows you, it sort of comes with a stylus and a doctor's blade, which sort of allows you to fabricate films with different thickness at different locations. A very versatile method, very simple, but it sort of allows you to make gradients. So, if you are, let us say, talking about a blend film or a block copolymer film with a flow coater, you vary the film thickness from one end to the other, you immediately get a variation in the morphology, which can get transferred to topographic gradient. So, gradients are very interesting and sort of they have quite a bit of application, and fabrication techniques are exciting and they are evolving. So, with that I think I will come formally to the end of this course on instability and patterning of thin films. Just a quick sum up, we talked about first about the applications of meso pattern surfaces, and then talked a little bit about surface related phenomena, because we are talking about surface patterning at mesoscale dimensions. So, after the course I expect that you understand what exactly is a thin film and how they are different from a layer of bulk liquid or bulk film, or so essentially we classified it in terms of where the interfacial interactions are active. And then first we focused a little significantly on different patterning techniques, and we argued that photolithography is one of the mainstays in the microelectronic industry, and though it is not particularly useful for patterning polymers, but having a good knowledge of photolithography is extremely essential, and therefore we discussed photolithography in somewhat detail. The other important aspect of photolithography, why it sort of still finds utility in patterning of in a course which talks about patterning of polymers, is at heart photolithographically you can generate structures which are sort of which actually can pattern only a photoresist layer, which is again a polymer. So, subsequently after photolithography we moved on to talking about different soft lithography group of methods which are the sort of very polymer specific techniques, and we introduced you to different types of patterns like topographic patterns, chemical patterns, and we showed that based on the soft lithography group of methods it becomes possible to create variety of structures. So, by micro contact printing, for example, it is possible to create chemical patterns by methods like nano imprint lithography, capillary force lithography, micromolding in capillaries. It becomes possible to create topographic structures. A flexible method like micromolding in capillary allows you to make structures not only in polymers but also in colloids, which is extremely exciting, and things like that. We also talked about a very novel concept of micro contact printing, MU-TM. We talked about micro transfer molding, which allows you to extend the soft lithographic methods for fabricating three-dimensional structures. So that's a very important aspect where you can create true 3D structures based on a soft lithographic approach at the meso scale. So after we discussed on direct patterning or the top-down lithography techniques, we eventually moved on to the instabilities. So we understood surface interaction, we understood the van der Waals forces, the intermolecular forces, their origin, how their scaling sort of changes between interaction of two particles to interaction of two surfaces. And in the meantime, we also had a detailed understanding, a reasonable understanding of one of the major characterization tools that is used for in these type of studies, that's the atomic force microscope, because we argued that we may be making these structures at the meso and the nano scales, but it's extremely important to examine the structures, and atomic force, there is no better way to do it than an atomic force microscope. If not for anything else, it's for the fact that you get a true true resolution in the Z, or you get the true height of the features. So we did that, and atomic force microscope again relies mostly on interatomic interaction, which is van der Waals forces. So we understood the nature of van der Waals forces, and then we examined how these van der Waals forces sort of amplify in an ultra thin film depending on situation to situation, leads to spontaneous disintegration or dewetting of ultra thin liquid polymer films. And we looked into the experimental aspects as well as the theoretical aspects based on the governing equation and the linear stability analysis. We understood how the sign of the effective Hamarker constant sort of determines, or the partial derivative of phi with h, that's del phi del h, that's the variation of the effective interface potential with h sort of plays a decisive role theoretically on the stability and dynamics of a system. We understood the roles of individual parameters. We understood how surface tension opposes any sorts of instability, surface undulations. We understood that how viscosity, for example, has an important role. It sort of controls the dynamics of the system, but it can never induce instability. We also looked at what are the sequential events under which a film can eventually become unstable, and saw that how surface tension sort of undergoes a role reversal from an opposing role before the film ruptures to a role where it actually favors opening up of a hole. Then we looked at the various aspects of dewetting stages and looked at the different morphologies, so formation of hole, growth of holes, the formation of rims, coalescence of rims, formation of ribbons, and breakage of the ribbons into isolated droplets. We also talked about the role of viscoelasticity and slippage on dewetting, and how the morphology sort of differs in cases where you have significant slippage, or how the effect of viscoelasticity becomes prominent as compared to dewetting of a film which is in a purely viscous regime. And subsequently we argued that in the last few classes that instability in the we also did mention about some special cases. One of them is a bilayer instability, how depending on which of the interface becomes unstable first, how the overall morphology of the system can be significantly or strongly influenced by that. We also talked briefly about strategies to work out strategies to suppress dewetting, because this type of instability can be very exciting from the standpoint of basic physics as well as for some mesoscale pattern formation. But from the standpoint of a coating where a thin film finds maximum application, this is completely undesirable. So we talked about suppression of dewetting, and one of the approaches we talked about is by addition of nanoparticles, where we argued that the addition of these nanoparticles sort of locally alters the rheological properties. And finally, we talked about one of the limitations. So, we argued that in a instability mediated process, you have additional handles or tuning parameters like film thickness, etc., by which you can control the pattern geometry, pattern order, things like that. So, let's say the periodicity of the structures can be influenced by issues like film thickness, surface tension, and things like that. Also, to the extent you allow the instability process to run, you can quench the process at any intermediate stage. You can take advantage of the fact that most of the nonlinear techniques, nonlinear methods have multiple steady states. So, you can sort of drift your technique in one of the directions, and you can sort of hop onto any metastable minima to stop the process, to stop the evolution at that stage. But most of the instability mediated techniques sort of lack long range order, and for that we have talked about in the last couple of lectures about how these instability mediated structures can be aligned by suitable templating strategies, which include use of topographically patterned stamp or substrates, which is a combination of self-organization and the top-down lithography techniques, eventually resulting in aligned instability structures. And in the last lecture, as a special topic, I just introduced you to the concept of gradient surfaces. Hope you enjoyed the course. Thank you very much for attending.